Okay, welcome back everybody. I'm going to do a little whirlwind tour of constellations. Hopefully at this point you've seen the Carl Sagan video that I linked. If not, please watch it right after this. Nobody can contextualize stuff like Carl. So first, just a quick little definition here, a little video from the History Channel to explain us the basic definition.
From the Latin base co, meaning together with, stella, meaning star, the word constellation means a grouping of stars. Mapped out like a blueprint, constellations are patterns for the billions of stars that are scattered across our sky. Based on mythological stories of Greek gods, creatures, and animals, our heavens have more tales to tell than hieroglyphics at Giza.
Not sure about the soundtrack.
The meaning and movement of constellations were deeply rooted in Greek culture. Among them, Orion, the hunter, was said to have encountered a venomous scorpion. To escape from the creature, he jumped into the sea, which to the Greeks explained why the constellation Orion appeared from November to March, but disappeared as Scorpius rose to sting him.
Okay, the graphics are not so good anymore. This is the kind of backstory that I want on your quarter project.
Night sky change positions throughout the year. Why does this happen? The Earth spins on its axis, moving east to west, so objects appear to rise in the east and set in the west each day from our vantage point. As Earth continues its path around the sun, different constellations become visible at night, as the sun appears to be in different parts of the sky. There are a total of 88 recognized constellations by the IAU, 12 of which are zodiacs. Zodiac constellations differ from the rest of the 76 because they cross the path of the ecliptic, which is the path that our solar system's planets travel along each year. Because these constellations were so-called touched by the sun, Babylonian astronomers thought they bore significant importance.
Touched by the sun. Come on.
While viewing constellations, make sure to bring a Greek mythology book so that you can read the many tales of heroism and tragedy that these legends endured in order to earn their place.
That makes no sense. Like you'd have to have a flashlight or a bright light source to read it by. It could ruin your observation. Okay, so this idea of the constellations, sort of being of importance. I like this video because there's no audio or anything. I think it might have a soundtrack. I don't know. But they appear the way they do. Like here's the Big Dipper, right? And it, looks like a big spoon or something like that. But, this is the way that these stars, they're not connected with lines. That's something we're doing. And these stars just look that way from our vantage point. So these lines will remain constant that are connecting stars that, like a connect the dots game that people do to make the constellations. So we're going to leave those lines the same. And as this video pans out, you'll see the true shape of the constellations when you leave Earth. So at first, when you're close to Earth, they don't change that much, right? But then when your vantage point gets far enough away, outside the solar system specifically, you'll see it all distorts. Right? And so at the very end here, you're seeing the whole Milky Way galaxy. Let me run through that one more time for you. So as it pans out, you're panning out from the solar system, and eventually you'll see the whole Milky Way galaxy. But about halfway through, you'll see that all of these bright stars are in our local neighborhood within the galaxy, and they're all at kind of random spots, actually, right? And they don't, when you pan out this far, you can't even see them anymore. So it really is that the constellations are completely dependent on our perspective, right? So when we look at the W that makes up Cassiopeia and we see these stars and we draw lines between them in our mind and we say they look like a W, that's because we're looking at them in a certain vantage point and they look like they're all side by side like this. But the truth of it is look at how distant, varying in distance all these stars are. So, some stars in some constellations may be close together. They may be related. But they don't have to be, right? They just appear in the same sector of the night sky, and something that's really bright but far away can look just as distinct to us as something that's dimmer and closer. And so this idea of the constellations, although it's fun and it's a useful way to categorize stars and to recognize patterns and stuff, the utility of them in sort of understanding the Milky Way galaxy is kind of minimal. So in ancient times, right, they had 48 constellations, basically heavily favoring the northern hemisphere because we get most of this from the Greeks and the Romans, who are northern hemisphere cultures. And they had 48 constellations, and those are the ones that we probably know the best through literature and stuff like that have these stories associated with them that go back to antiquity. Of course, every culture, indigenous population, had their own sort of like patterns that they saw in stars and have their own constellations. And I believe in the Carl Sagan video, he walks you through that. I think that's very interesting how different cultures will look at the same set of stars and like a Rorschach test, they project different items in there. But in modern times, so the IOU has divided the entire sky as visible from Earth. Imagine I'll show you a picture here in a second. Imagine like a sphere that we're embedded in that has all the stars in there. And they basically have cut it out, trying to honor these traditional constellations into 88 constellations. And so that's the IAU, the same governing body, I believe, that demoted Pluto to a dwarf planet. They're the governing body that determines these sort of like, definitions and arbitrates where the lines are and things like that. So here's a picture of the celestial sphere, as I was saying. So if you imagine putting a point of light, equal distance, which of course is completely false, but that's what it looks like to us from the Earth for every star that we can see with the naked eye. So all the constellations for both the northern and southern hemisphere are points of light in here. And this is what the IAU has divvied up into like 88 kind of like puzzle pieces, right? Because they kind of respect the existing constellation. So this helps explain how stargazers actually define where they want to point their telescopes or tell people where to look. So you can see that if you think about this larger celestial sphere as being just another kind of Earth-like thing, you can project latitude and longitude on there, except how far up or down you're going to look, which would be the latitude lines, is called declination. And then as you want to go left to right over here, those are called the right ascension coordinates, right? So stars are located instead of by latitude and longitude, like we locate things on planet Earth, we locate them in the sky by declination and right ascension, but they serve basically the same purpose, right? So declination works this way. If you want to look at something that's right above the equator, that's considered to be 0 degrees. And then as you angle towards the North Pole, or technically the celestial North Pole, that is the point above the Earth's North Pole, right, in space, that would be positive 90 degrees. And then you go down to the southern hemisphere, that would be negative 90 degrees. So the declination is measured in degrees, right? Because you're basically angling up or angling down to locate a certain spot in the sky. Now, the left to right is interesting. That's the right ascension piece. The Earth goes around, right, once every 24 hours. And so they just kept those units of time, right? So instead of doing degrees, they do right ascensions in hours, minutes, and seconds. So from 0 to 24. And the 0 hour is defined to be the location of the sun at the vernal equinox, right? And so everything is mapped out, if you like, in right ascension terms from that point forward. Of course, over a given night of stargazing, if you wanted to look at a certain star, the declination would remain constant over the course of that night as the star kind of appears to travel across the sky as the rock you live on rotates, but its actual location in the right ascension sense is changing all the time, right? So here's some other definitions that go along with this. So a lot of the things that people talk about as constellations are actually technically asterisms. So, for instance, if people talk about Orion's Belt or the W in Cassiopeia or the Big Dipper, which is part of Ursa Major, they're highly recognizable kind of subsets of constellations. There aren't 88 asterisms, right? There's far more than that because there are 88 constellations. Constellations are rather pretty big. So an asterism is a recognizable part of a constellation that has its own name. Now, the constellations themselves can be kind of categorized into roughly 3 groups. And if we go back over here, so you've got these stars that are up here kind of hanging out near the celestial North Pole. These stars are only visible from the northern hemisphere, right? If you live down here and anywhere in the southern hemisphere, you'll never see any of those stars, right? Because the entire planet is kind of blocking your view of them. And likewise, those of us that live in the northern hemisphere, we're never going to see any of these southern stars or southern constellations that are near the southern South Pole. And so those are called the circumpolar, right, around the polar region, constellations, right? And the other way of thinking about, in addition to which ones we cannot see, is that these ones, for us in the northern hemisphere, the northern circumpolar constellations, are visible any time of the year, right? As long as you have good nighttime viewing and you look kind of towards the north, you're going to see some of the familiar and most famous constellations. A lot of those 48 ancient constellations are the zodiac ones, which I'm about to talk about in a second, and the northern circumpolar ones. And the poor southern hemisphere ones, just, nobody had seen them back in ancient times that we inherited those cultures from, Now, so you have 2 circumpolar regions, right? The southern and the northern. And then the ones in the middle, the equatorial constellations, those are interesting because if you're hanging out near the equator, you are probably visible from both the northern and southern hemisphere, right? People in the north would look towards the south to see those, and people in the southern hemisphere would look towards the north to see them. But these are also, of course, since everything in the solar system is in a plane, this is the ecliptic, of course, is very close to the equatorial line, right? We've got that slight tilt that gives us the seasons. But we have all of the planets and the sun, which is the most important part of the story, are hanging out in this plane. So that means at different times of the year, the sun is going to be in different quadrants of the equatorial constellations. And so these are only visible seasonally, right? So for instance, in the summertime, we're hanging out on one side of the sun. We're not going to see a certain set of equatorial constellations. And then on the other side, 6 months later, we're on the other side of the sun and we see them and we don't see the ones that we saw 6 months before, right? And so those would be so let's walk through this from top to bottom, right? So we're basically going to go in slices. We're going to do this, the circumpolar and the north, and then we're going to go through the 4 seasons of equatorial. So you can imagine sort of like cutting the 4 equal pieces out of the sphere near the equator. And then we'll do the southern one. So northern circumpolar constellations, you got some pretty famous ones, Ursa Major, Ursa Minor, Draco, Cassiopeia, right? Now this star here is a pretty famous star, which I have a slide on later, but think about why that would be so different. If you're hanging out directly above the North Pole, what is going to be different from our perspective on Earth when we look up at you over the course of the night? Just think about that. Okay. All right, so here's another view, same thing, right? These are the circumpolar stars. They're not visible from the southern hemisphere. That special star I was talking about is right here. That's called Polaris. And notice that over here, you can see this kind of white band over here. That's a portion of the Milky Way. This is the part of the Milky Way that we see from the northern hemisphere. And notice that it's, if the viewing conditions are right, you can always see the Milky Way. In fact, it'll be the only common element in all of these pictures. So dropping all the way down to the south, let's do the opposite side of the planet Earth. So this is right above the southern pole. The celestial South Pole doesn't have any star there, so they don't have a corresponding Polaris star, or what we would call the North Star up here in the northern hemisphere. But they can see other things that we can't see, like the Large Magellanic Cloud, which we now categorize as a dwarf galaxy. And they have spectacular views of the Milky Way. You can see the Milky Way is a little bit thicker and a little bit more visible in the southern hemisphere. And then here are the equatorial constellations. These are what you can see in the fall season. So you can see these stars. Here's the ecliptic, so you'll recognize all of these as being signs of the zodiac: Capricorn, Aquarius, Pisces, right? So these are the stars, these are the constellations and the stars that are visible when we're on one side of the sun that corresponds to our fall season. Then going into winter, right? Let's find the ecliptic. Here's the ecliptic again, right? So you can see Pisces is coming out of view, Taurus is coming into view, right? Got different stars here. And then when you get to the spring, what do we see here? Virgo, Leo, right? Cancer, Gemini, and then all the way around to summer, right? And you can see some of these summer constellations. So when people talk about the seasonal variation in constellations, they're talking about these equatorial ones, right? And way up here in the northern hemisphere, we can always see those constellations that we started this slideshow with. If you look, the stars don't have their names on here. They've named the constellation in this view, and they have these Greek letters. That's also part of your Q2 project, right? That's the bear, the so-called bear designation named after the guy who did it. And he just basically went through the Greek alphabet with, so the alpha designated star is the brightest star in that constellation. And he basically just categorized them by their apparent brightness from Earth. So the zodiac. So let's talk about the zodiac, right? Because this is where the overlap between astronomy and astrology comes in. There are 13 constellations that overlap with the plane of the ecliptic, right? So if you go around and follow the ecliptic through the 4 seasons, you'll find that it slices through 13 different constellations. And so the fact that the sun blocks your view, from Earth, it appears as though the sun is passing through that constellation, which of course is not true, right? It's just in our way. And that is how the astrologists assign the zodiac sign, right? So if you're a Pisces, you're born in like late February or whatever, and that means that the constellation Pisces is not visible. It's the one that the sun is blocking the view of the most during that month, right? And for some reason, astrologers, I think because there's 12 months of the year, so they picked up only 12 out of the 13 constellations. So there is this one equatorial constellation, Ophiuchus. I don't know what it is, right? Because nobody ever talks about it. Poor guy got neglected between Scorpio and Sagittarius, right? So I don't know the entire history of why they don't use that one, but I think it is probably nice for them to say, oh, we've got 12 months of the year, and so let's have 12 constellations, one for each month that can give us the sign of the zodiac, right? So a couple other just random tidbits about stargazing and constellations is that most of the stars that you can see in your naked eye, so that means most of these constellations stars, are actually not single stars, right? They're double stars or sometimes triple stars and very rarely quadruple stars that are in a system together, right? They're orbiting around their own common center of mass. But they're so close together that unless you have a high resolution telescope or something, you can't see them as separate stars. They just look like a single point of light, right? For instance, Polaris and Alpha Centauri, I believe, are both triples. And the other thing that's interesting is when we look up there, when we see all those stars, we're of course seeing the brightest stars and the closer stars, right? If the farther stars away, if they're not bright enough, we just don't see them at all. Or they could be really bright and really far away, in which case they just kind of blend together with other very distant bright stars. In fact, that's what the band of the Milky Way is, right? That solid, kind of milky looking fuzziness is just the light of literally millions or billions of stars that are just too far away for us to discriminate the individual points of light. But the thing I wanted to say was that we estimate that something like 85% of the stars in the Milky Way galaxy are these single red dwarf stars, which are so dim that we cannot see them with the naked eye. So when you're looking out there at the constellations, you're missing the majority of the stars, right? Because the most common star type is the red dwarf. Why is it the most common? Because they live so long. Remember when we were talking about that? And because they're the lightest mass, so they're the easiest to form, and they're the longest living, so they're the most common star. But the poor guys just aren't bright enough to be seen from Earth unless you have a telescope. Okay, the other thing that you'll see in these star maps, or that can be observed with the naked eye, are kind of fuzzy points of light, like this is a hint, a clue to what they are. They're like mini Milky Ways, right? And this guy named Messier went through and systematically categorized them and said, this is not a point of light, it's not a star. And so they became known as Messier objects. And if you look at star maps, they'll have an M in front of them. And at the time that he did it, we didn't know what they were. And so, like, for instance, M31 is one of the most famous Messier objects, and it is visible with the naked eye. I believe you have to be in the southern hemisphere to see that, though. And we now know that a lot of those are actually entire galaxies. They're not actually within our Milky Way galaxy. So they could be a cluster of stars, or it could be a big gas that's being lit by internal stars, and you can't see the internal stars. That would be a nebula or nearby stars. Or it's a bright, distant galaxy, right? The Andromeda Galaxy being one of the closest ones. And the large and small Magellanic Clouds are also considered to be galaxies, also only visible from the southern hemisphere. And of course, our own Milky Way galaxy, if you go back through here, why is that embedded in all of these different things? Is because we live inside the Milky Way galaxy, right? So in any direction that you look, you're going to see that band of white, right? The Milky Way galaxy is just there because, like we're a speck in the batter of a pancake, basically. So getting back to Polaris, the North Star, right? This is the answer to the question that I asked you earlier. This is a 2.5-hour time-lapse photography from one of the mountains in Hawaii. And as the stars appear to move across the sky, right, they would take 24 hours to go around in a complete circle. Of course, we don't see them during the daytime, but that's why you see this is a single star, for instance, if you follow this track, right? A single star moved from here to here in the 2.5 hours that this camera lens was open. And as you get closer and closer to looking right above the North Pole of planet Earth, that is the North Celestial Pole, the circles are getting smaller and smaller, right? And that's because this motion, this apparent motion, is not due to the stars moving at all, right? It's the same reason why the sun and the moon appear to rise and set. It's because we're on this spinning rock, right? And the North Pole of our planet is pointed right over here at Polaris, and you can see it is barely moving at all. It's on such a small circle, and that's because our North Pole is pointed almost directly at it. And so that is called the North Star, because if you can find it, it's a relatively bright star. And it is always, unlike the other stars, which may be changing position over the course of the night, it's always going to be hanging out above the North Pole. So if you can see it and find it and locate it, then you can orient yourself to navigate by the stars. Okay, that is it for our whirlwind tour of constellations.